Hello, my name is Molly Flynn, and I am a junior in engineering physics. This summer I worked within the Nuclear Engineering and Radiological Sciences Department with Professor Karl Kruszelnik and Research Associate John Nees. I worked with writing the software for the Multiphoton Intrapulse Interference Phase Scan, or MIIPS. The motivation behind this project is that experiments in the lab are in the ultrafast laser pulse or femtosecond regime. When the pulse durations are this short, pulse distortions can occur. This leads to two main problems. First, the pulse shape is not consistent. This means that it's hard to obtain a high repeatability when performing experiments. Second, the pulse consists of many different wavelengths. The maximum power output or maximum intensity of the pulse occurs when each wavelength arrives at the same time. When pulse distortions occur, each wavelength has its own maximum intensity in the time domain. This means that the maximum power output or transform-limited pulse cannot be obtained. Thus, there is a need for a system that can both measure and correct phase distortions in our pulse, such as MIIPS. MIIPS first introduces a known reference function of the phase. It then adds this reference function to the initial pulse phase. Through mathematical theory, it can be shown that the maximum intensity of the pulse occurs when the second derivative of our initial phase is equal to the negative second derivative of the reference function. Thus, we can integrate the reference function twice to find the phase and measure the phase. MIIPS then scans through many different reference functions at all frequencies present in the pulse to find the transform-limited pulse. The reference function can be added by a number of different instruments. Our system uses grading pairs. The reference function is adjusted by increasing or decreasing the spacing between the grading pairs. The setup is shown in the bottom right corner. The function created by the grading pair is a well-known group delay dispersion, or GDD. This GDD is described by a simple equation, making it easy to calculate. It is also easy to adjust. We interact with the grading separation by moving motors. The motors are programmed using a platform called LabVIEW. The LabVIEW uses a very visual programming language called G. Its advantages are that it's easy to use with instruments, such as the spectrometers and motors present in our system. It incorporates extensive support for the hardware. It is also easy to plot the data from the instruments. The disadvantages to this platform is that it's hard to tell the sequence of the steps in the program, and it is also hard to find errors in the program. The MIIPS algorithm follows the following steps. It first collects the spectrum data at each grading separation. The spectrum data consists of wavelengths and their corresponding intensities. It then finds the grading separation for the maximum intensity of each wavelength. It evaluates the group delay dispersion, or reference function, at each of these separations by calculating the equation. It then subtracts the group delay dispersion at a best grading separation. The best grading separation is the grading separation found during a previous MIIPS routine. If this data is not available, the best grading separation is then the median value of the possible grading separations. It then integrates the group delay dispersion with respect to frequency twice to find our initial pulse. The program then outputs 4 graphs. Here is a sample output of the program. The most important of these 4 graphs is in the upper left-hand corner. This is the graph of phi, or our initial pulse. If this pulse were to be transform limited, then the graph of phi would be a horizontal line at 0. As can be seen, this pulse is not transform limited. The MIIPS routine will then continue until the closest to this transform limited pulse, or horizontal line at 0, is found. This concludes my presentation. I would like to thank Professor Kruszelnik and John Nees for giving me this opportunity this summer. I would also like to thank you for viewing my presentation.